In this video, we will learn how to determine the empirical formula of a compound based on either masses that were determined experimentally or mass percent composition. In a later video, we will learn how to take our empirical formula and turn it into a molecular formula. So there are lots of different experimental instruments that exist out there, analytical instruments that exist that can tell us what the mass percent composition is of our sample. It will tell us what percent of each element is in each sample using a variety of different methods. You could have a mass spectroscoper, gas chromatography, atomic spectroscopy, wavelength dispersive spectroscopy, X-ray dispersive spectroscopy. This is on an electron microprobe instrument. I use this middle one here. I don't have much experience with the gas chromatography or atomic absorption instruments. But anyway, there's a whole bunch of fancy analytical equipment out there that will tell us how much of each element is in a sample. From that, we have to backwards calculate how much or what the empirical formula is of the substance that we were analyzing. So in this video, we will learn how to take our mass percent composition or masses, turn that into moles, find the lowest whole number ratio of the elements, and that will give us our empirical formula. In a later video, we will learn how to take our empirical formula and turn it into a molecular formula if we have a molecular compound and we know the molar mass of that compound. So as I mentioned, I used the middle instrument, which was the wavelength dispersive spectroscopy, when I was in graduate school in order to analyze samples. So really briefly, what I researched when I was in graduate school was I made materials that were going to be used in radioisotope thermoelectric generators. So I didn't actually make the full radioisotope thermoelectric generator. I just made a material that would go inside. So what this radioisotope thermoelectric generator does is it has a radioactive element, such as plutonium, that produces a lot of heat when it's decayed. And this radioisotope thermoelectric generator, RTG, converts that heat into electricity to power things like this spacecraft. So this is a deep space probe that has been launched into outer space. This technology has been around for a while. It just hasn't been very efficient. But they can't use solar panels when you're in deep outer space because solar panels require sunlight. And when you're too far away from the sun, there's just not enough sunlight to do that. So this RTG is the main way that these deep spacecrafts are powered. So I made a material that went inside of there. And I had to do experiments to not only make it, but experiments to verify that I thought what I made was what I was hoping to make. So here's some experimental data, and we will do some calculations to figure out what the chemical formula of this is. Now, I'm going to calculate these in the order that we would write our chemical formula in. And so normally we write the leftmost group first, and in this case that is ytterbium. Because we have to remember that the rare earth elements are actually inserted before most of the D block elements like manganese. Antimony is farthest to the right, and so that will go last in our chemical formula. So the first step to figuring out this chemical formula is to convert each of these percentages into a mass. And so if I assume that I have 100 grams of it, then 63.85825% of 100 is just going to be 63.85825 grams. And so then I have to get that into moles. So convert to mole. And so I need to cancel out my grams and I need to get into moles. And so this is my molar mass. Whenever we need to convert between the use of grams and moles, we use molar mass. And so that is 173.04 grams per mole. So I'll go ahead and calculate that. That's 63.85825 divided by 173.04. And so that is 0.36903 moles of ytterbium. And so then we'll do the same for manganese. Maybe I should have left myself a little bit more space. Okay, so manganese was 1.447722 grams. So I'm assuming I had 100 grams like before. And I'll use the molar mass of manganese. Manganese is atomic number 25, not to be confused with magnesium. And so that's 54.94. And so that is 1.447722 divided by 54.94. That is 0.026359 mole of manganese. And then lastly, we have antimony, which is 35.3938 grams. And then I will convert that into moles by using the molar mass of antimony from the periodic table. So look that up. And so that's 30. Oop, back. Hit enter first. Okay. 35.3938 divided by 121.76. 0.29. It's supposed to be a 0 first. 0.68495 mole of antimony. Now, these are really ugly mole amounts, but our subscripts in our chemical formula do relate individual counts, and we can scroll that individual counts up to moles. And so this equates to 0.36903 of ytterbium, and then manganese would be 0.0263509, and then antimony is 0.2906849. So these are really hideous subscripts, and we always report subscripts as the lowest whole number ratio. And so we can't just leave it like this. So we got to scale up things so that the smallest thing is at least 1, because the smallest subscript we can have is 1. So this is the smallest subscript here. And so our goal is to set this equal to 1. How we can set this equal to 1 is dividing it by itself. And so now our manganese subscript would be 1. But in algebra, they teach you that if you do something to one side of the equation, you got to do it to the other side of the equation. So now we have to divide the same by the same thing all across the board. Okay, so I don't have enough room to keep writing, so I'm going to keep writing up here. And so I got to write my new subscripts. Now I know my manganese subscript is 1. So I got to take these other numbers and I have to divide by the smallest. And so I'm going to test out this on my calculator. No, that's not what happened. Okay. So I haven't learned how to use this calculator app too well, but most calculators have the ability to store numbers and to recall numbers. But I have to play around with this app a bit more to figure out how I'm supposed to store them correctly, because when I tried to do it before, I couldn't figure it out. So I'll have to play around with this. But I will go ahead and do it, just manually typing it in. I wrote out a bunch of digits, but since I never round answers until the end, really I should be using the full numbers. So that's really close to 14. So that's ytterbium 14. And so that's about equal to ytterbium 14, manganese, and then we don't write subscripts of 1. I'm just going to clean that up a little bit. And then let's figure out what antimony is. Okay, so antimony was 0.2906849 divided by 0.0263509. And so that's 11.0313, which is about equal to 11. So the chemical formula of this compound was ytterbium 14, manganese, antimony 11. Here's another example problem. In this example, we won't end up with nice whole numbers of subscripts right away. And so this is another example to show you how things can get complicated. So it says a sample of the mineral magnetite contains 3.79 grams of iron and 1.45 grams of oxygen. What is the empirical formula of magnetite? So we don't need to convert these into mass percent composition because we already have masses. And so I can just start by taking my 3.79 grams of iron, and I have to first convert that into moles. Because my subscripts do not relate masses, they relate to moles, or counts of things. So that's the molar mass of iron. So 3.79 divided by 55.85. And so that is equal to 0.0678034. We'll call that good. Right, I'm going to try to store this, but I don't know how that works on this calculator. I don't know what that does. Okay. Well, I got to play with this out more. All right, we got 1.45 grams of oxygen, and we got to convert that into moles, and so that's 15.999 grams. What's funny is that if you use the same elements enough, that you will actually memorize the molar masses, even though no one asked you to. It just happens. Because you use the number too much. So that's 0.0906306. Okay, so these are really hideous subscripts. And so that works out to iron 0.6780. Sorry, I forgot the 0 there. Very important. And then oxygen was 0.0906306. Okay, so the iron one is actually less because that's 0.06 and that's 0.09. So I got to divide both by the iron's subscript in order to turn the iron into a 1. So I got to take my oxygen amount and then divide it by 0.678034. Okay, and so that turns me into iron. I'm just going to write the 1 there so that I can remember right now. Okay, so looking at this, that's about 1/3 of an atom because 1/3 is 0.33. So that's like one and 1/3 oxygen atoms. And so if this is 1 and 1/3, then I gotta multiply this by 3 in order to get a whole number. And so that if I do that to this oxygen, then I gotta do it to the iron as well. And so that's Fe3, and then I gotta multiply that by 3, and so that turns me into oxygen 4. And so now my lowest whole number ratio, my empirical formula, has whole number subscripts. So Fe3O4. If you are wondering about the ion charges and thinking about this chemical formula, how we end up with this chemical formula is actually a mixture of iron 2 and iron 3 plus ions. So it's a kind of a mixture of the two different cations charges, in case you were curious. So this table here is to help you kind of identify if you see these decimals, then it relates to a fraction with this denominator. So that kind of tells you what you need to multiply by in order to clear the fraction. So if you see like 1/4 or 3/4, then you should multiply by 4 in order to make things a whole number. If you see things end with just 0.20, 0.40, 0.60, 0.80, those are related to fifths, 2/5, 3/5, 4/5, and so you need to multiply by 5 in order to get back to a whole number. You always multiply by the denominator of the fraction to make it a whole number. So recognizing these common fractions in decimal format can help you identify what you need to multiply by in order to get back to a whole number. Here's a practice problem for you. It reads, beta-carotene is an orange pigment found in carrots and other orange plants like pumpkin. It is 89.487% carbon and 10.513% hydrogen by mass. What is the empirical formula of beta-carotene? Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to continue and check your work. Okay, let's get going. So if I assume that I have 100 grams of beta-carotene, then I can just turn these percent signs into grams. And that will give me a mass to start with. And so that's 89.487 grams. And then that's grams of carbon. So I gotta look at my periodic table and find the molar mass of carbon, 12.011 grams per 1 mole. My grams cancel out, leave me with moles. 89.487 divided by 12.011, 7.45042. You can just write out a lot of digits here. You don't have to worry about sig figs because we never round intermediate calculations. And all of this is intermediate calculations. So for hydrogen is 1.008 grams per 1 mole. The grams goes in the denominator so that we can cancel out grams and be left with moles. Okay, so 10.513 divided by 1.008, and that is 10.42956. So that's bigger, so that's 7.45042, and hydrogen 10.42956. So carbon is smaller, and so we have to divide both of them by the smaller value in order to turn the smaller value into a 1. And so that's carbon 1, and then this number divided by 7.45042. Hydrogen 1.39986. Okay, so this is about equal to carbon 1, hydrogen 1.4. And a 0.4 is 2/5. And so that's 1 and 2/5 hydrogen. So to clear this denominator, I have to multiply both by 5. So if I multiply 1.39986 times 5, it should give me something that's essentially a whole number. And so 1 times 5 is 5. Oh, I made a line. So C5, and then hydrogen will be 7. Because 6.9999 is essentially 7. So beta carotene's empirical formula is C5H7. All right, one more. Never mind, not one more.